Okay, so I believe we are now live. So it's a pleasure to be here with Jean-Claude Bouret. So good afternoon, everyone, and good evening, Jean-Claude. And thanks again to accepting the invitation. It's 7 p.m. in Marseille right now. So
Yes, it
thanks a
is.
lot. It's dinner time actually, but he was kind enough to accept the invitation to talk this late. So, okay, so I will start presenting Jean-Claude a little bit. So he got his PhD in Grenoble, France in 99. And then after his PhD, he went to the US, the Goddard Space Flight Center at NASA. So he stayed there for 3 years, working on massive stars. And then later in 2004, he got his permanent position at the Seminários, which is a same thing as the CNPq here, but in France. In Marseille, at the Laboratoire d'Astrophysique de Marseille. So since 2004, he's working there mainly on massive stars. He's expert in stellar atmospheres, stellar evolution, anything regarding mainly massive stars. Okay, so and he also a co-eye of Pollux, which is an instrument that will go hopefully aboard the LUVOIR telescope, and magnetic fields as well of massive stars. He's a specialist too. So he's a reference in the field. He's also a friend of mine for a long time. I've been in Marseille. I worked with him. So Jean-Claude, please, I will remove myself here and you have the presentation for you. And thanks again. Okay. When you finish, I will come back. And if the audience has questions, the audience will post here and then we will see. Okay.
So, by the way, Wagner, I don't think I remember if you told me how long do I have? Like 45 minutes?
Yeah, more or less, no problem. Okay.
Okay, sure. Thank you.
Okay. Thanks again. I really appreciate your acceptance to be here.
No problem. As a matter of fact, yeah, it's late, and it's not only dinner time. It's just that in 2 hours from now, there's a football game between France and Germany, so I don't want to miss it.
Okay.
So I'm gonna make sure that I will fit in less than 1 hour, so that then I can move
Enjoy
to the big game.
Okay.
To the big game. So yeah, good afternoon, everyone. It's a pleasure to be here online with you all for the seminar of the Valongo Observatory. So before I start, obviously, I want to thank Wagner for inviting me to give this seminar. And of course, I feel quite unlucky that I have to give it online and not in person in Rio, since I never had a chance to visit Brazil. But who knows, maybe I will have another opportunity in the future to come and visit you guys. So my seminar will focus on the Ulysses legacy program, from the original ideas to the first data releases, and I will try to illustrate some aspects of the science that Ulysses will enable. I should mention that I received a lot of material from Julia Romandival for the preparation of the talk. Julia is the lead of the Ulysses core implementation team. So what is Ulysses? Ulysses is a discretionary program of the STSCI director, Ken Senbar. And more precisely, Ulysses was selected by Ken Senbar following the recommendation from the HST UV Legacy Science Definition Working Group to his charge to identify a large legacy UV program focused on star formation and related stellar physics. And this is in the context of the HST UV initiative. So Ulysses is the acronym for this very long title there. And it should serve as a UV spectroscopic reference sample for high mass and low mass young stars. So another recommendation from the committee was to make it such that Ulysses would be allocated up to 1,000 orbits of HST time, and that it would be divided as equally as possible between high mass and low mass stars. And by doing so, the committee expected that Ulysses would deliver a definitive UV dataset on the first 10 million years of stellar evolution. So the recommended library should provide observations that uniformly sample the fundamental astrophysical parameter space for each class of star. So for massive stars, this is spectral type, luminosity class, and metallicity. And for low mass stars, it's going to be spectral type, age, and disk accretion rate. Key elements of the program include extending template spectra of massive stars to low metallicity regimes, such that studies of high redshift universe will become possible. And concerning the young low mass counterparts, it's going to be the goal will be to extend the reference spectra for young low mass stars and brown dwarfs all the way down to below 0.5 solar masses. So this is a summary of what I just said. So Ulysses is a UV spectroscopic survey of young, low, and high mass stars. So, so as you can see here, it's divided in two again. So the high mass counterpart is 500 orbits pretty much to extend the spectroscopic library of O and B stars to low metallicity. So typically from less than a tenth solar to 1/half solar. By doing this, you're going to study the properties of massive stars. So you're doing stellar physics and studying the wind velocities, clumping, mass loss rates, CNO abundances, and test evolution models. But you're going to be able to study, to provide spectral templates useful for population synthesis and studies of the escape of Lyman continuum photons, for instance. You're going to be able to study ISM abundances and dust depletion, and then study the evolution, the chemical evolution of the ISM, and pretty much the same kind of studies you can do in the CGM between the galaxies that will be observed, so the Magellan clouds essentially, and our own galaxy. So this is a spectrum on the left of a B star that was observed in the framework of Ulysses already. And here on the plot are identified some critical regions, both for stellar physics, so the stellar wind, with typical PCD profiles, and for ISM and CGM studies. Concerning the low mass counterparts, again, about 500 orbits dedicated to obtain spectroscopic library and time monitoring of T-Tauri stars. So stars, young low mass stars, and by young I mean younger than 10 million years, typically. So again, you see a spectrum with lots of emission lines, especially in the UV. For a cool star, you don't expect emission lines in the UV, and this is the results of a powerful accretion, and I'm going to say a few words about that later, quite immediately after that. And so Ulysses will enable kind of transformative research on the accretion and ejection physics. And it's going to be useful also to study the evolution and dispersal of the accretion disks, and also to constrain the disk chemistry and planet habitability. So just a few words on young low mass stars. And so I'm going to say just a few words here because this is not my area of expertise. And for the rest of the talk, I will focus mostly on massive stars. So, this picture here shows you that at ages around below 10 million years, low mass stars have accretion disks that emit strongly in the UV at the location where the accretion flows reaches the star. So on the bottom, on the left, you see a schematic representation of an accretion column. And so when the gas reaches the star, so the infalling gas reaches the star, it creates a shock. The shocks creates itself X-rays, and the X-rays hit the gas in the pre-shock region and in the photosphere below, and the reprocessed X-rays emerge from that, mostly in the UV, and that's what you see on the spectra on the right, where in blue you have a typical spectrum of cool star without a disk, and on top of that we have the spectrum of a young star with an accretion disk, and you see the strong contribution of the accretion in the UV. The UV radiation is extremely important. It's a key parameter to understand the disk chemistry, its ionization, its evolution and dissipation. And it can be used as well to study the chemical composition and atmospheric escape of young planets, for instance. So what about hot massive stars? Why should we care about them? So by hot massive stars, I mean stars more massive than typically 8 solar masses. And these stars, they end up their life as core collapse supernovae, leaving behind compact remnants like black holes and neutron stars. A fraction of these massive stars, when they collapse and explode as core collapse supernovae, they also they may produce long soft gamma ray bursts. Those stars are very hot and very luminous, so therefore they have a strong ionizing flux, so they are responsible for the ionization of H2 regions, for instance. And it is also expected that the first generation of stars was composed of a large fraction of very, very massive stars, and that would be responsible for the reionization of the first of the universe. Because they are massive, they can nucleosynthesize elements in their core all the way up to the iron peak. And these elements, for instance, cyano, they release them in the interstellar medium when they explode, or through their very powerful stellar winds during their evolution. And if you find a large population of massive stars, they can, in some cases, be responsible for what we call galactic winds. They can also trigger star formation by compressing the gas around them. So to this day, massive stars have been studied quite a lot, but we don't understand, there is no global consensus on the details of the evolution and the properties of such stars, especially at what is disturbing, it's no consensus at solar metallicity. At lower metallicities, these details are even more uncertain, and which is very disturbing because the metal pool region is now subject of a growing interest in order to understand the condition of earlier cosmic epochs and to ultimately extrapolate the prescription for physical properties of massive stars to interpret the intermediate and high redshift universe and eventually connect to the pristine generation of stars. So in the last few years, for instance, panchromatic surveys probing the cosmic star formation rate have shown that the SFR, the star formation rate, peaks around redshift between 1 to 3.5 typically, when the typical overall metallicity was between 0.1 to 0.2 of the solar metallicity. At this redshift, star-forming galaxies, they show numerous features of massive stars, like in their spectra, like O stars or Wolf-Rayet stars. So here you have two spectra. One is a stack spectrum of 449 spectra observed in the VUDF project by Lefebvre et al. And indicated are lines that are typical typically is found in the spectrum of a massive star, an O or a B star. As such, the massive stars, they are very important and very powerful probes to study the properties, and especially the star formation rates of these galaxies. So it is fair to say that our understanding of galaxy buildup hinges in part on our ability to characterize adequately the properties of massive stars in various environments, so in different metallicities environments. So coming back to Ulysses, a few words about the timeline and milestones that have been achieved up to now. So the whole project started in June 2019, when the CIT, so the core implementation team, and the SAC, so the Scientific Advisory Committee, were assembled. I have a picture of the people of the core implementation team that I may show you later. The SAC is composed of 8 people, equally divided in 4 for the low mass cool stars and 4 for the high mass stars, and I'm a member of the high mass counterpart, obviously. So I highlighted in bold some very critical milestones. So for instance, in July 2020, the website was opened, and you can find here the URL. And in March of this year, there was a second release of the data that was obtained for Ulysses, which includes, to my knowledge, 126 LMC and SMC stars. 115 were already obtained for the DR1 release, and they have been reobserved to improve the signal-to-noise ratio, plus 11 new stars have been added. By August of this year, it is expected the DR3 of Ulysses, which will include time monitoring of classical T-Tauri stars, plus the spectroscopy of stars in NGC 3109, which is a low metallicity galaxy of the local group. I'm going to say a few words about that later. Okay, I'm going to skip this one now. There is not much to say about it. Just to know that quarterly data releases are expected in principle. That's the schedule that has been adopted for Ulysses. The very first Ulysses observation that was obtained in early July 2020 with COS, the Cosmic Origin Spectrograph, in the 1096 settings. MPG 368 was observed. It's a 05.5 dwarf in the Small Magellanic Cloud, located in NGC 346, which is a giant H2 region at the core of the SMC. This star was chosen to observe this star with that setting of COS because the spectrum in black was a spectrum that was already obtained that was in the archives for this star, and it was obtained more than 10 years ago with this. But the far UV part of the spectrum was missing. So by far UV, I mean everything that is below 1150 angstrom, and that extends down to pretty much 1000 angstrom, which allows us then to cover very important lines for studies of stellar winds, like the phosphorus 5 lines that are essential to study clumping. And here, which is shown, the 06 1031 line, which is a super ion that is, when it is present in the wind of a star, in the spectrum of a star, it's telling you directly that lots of X-rays are produced in the wind of the star. So this is important to study the physics of the winds. Now, some details about the target selection. So stars in the Magellan Clouds are the primary targets because they represent in the local universe the closest analog to the metallicity conditions met at redshift around 2, typically. So when the universe was at the peak of the star formation, as I said before. So the distance modulus of the clouds are less than 60 kiloparsec, I think, for the SMC. But unfortunately, with the LMC and SMC, you can't go down in metallicity below, I think it's 0.5 salt. If you want to go down even further down, you have to go to galaxies of lower metallicities in the local group, which are much further away. So I surrounded the galaxies that are the targets of Ulysses. So NGC. So I forgot GC. So NGC 3109 and Sextant A. There are also some spectra of stars that have been obtained for IC 1613 and WLM a few years ago. So the table on the right shows you the metallicity of the star, and more exactly, it's not the metallicity itself; it's the log of O over H, which is the closest analog we have for the metallicity. Because for those stars, they are so far away that so far it has been very difficult to obtain a high signal-to-noise ratio, high resolution spectra, so that we could measure directly the metallicity. By metallicity, I mean measuring the iron content, for instance, in the spectrum directly. So it's very challenging, even with an instrument as powerful as HST, to observe those stars. Next. Okay. But anyway, those stars, they are part of the Ulysses program. So 240 targets will be observed by Ulysses, and there are about 90 to 100 stars that are already in the archives. But that will be also included in the Ulysses database at the end. So 497 orbits are dedicated for massive stars, 451 for Tetori stars, and there will be also 2 orbits for pre-imaging of the stars in Sextant A and NGC 3109, because those galaxies are so far away that we need pre-imaging to make sure that we target the right star. So the selection process followed not as objective, as reproducible, and transparent process as possible. The process and outcome of the target selection was documented, and it was reviewed by the Science Advisory Committee. And the targets, they were released to the community on February 2020. So you have here on the table the total number of stars that have been selected for Ulysses. Just a few words about the low metallicity massive star sample. So as I said, these galaxies are very far away, so it's only possible to observe 6 stars total at high enough signal-to-noise ratio with a high enough spectral resolution. And by high enough, I mean above 15,000 typically. And still observing 6 stars will require 50 orbits of HST, which is quite a lot. I don't know if you already applied for HST time, but it's just obtaining a few orbits is already quite difficult. Concerning the LMC and SMC, so the shortlist of targets were selected for both the LMC and SMC in each bin of spectral type and luminosity class, based on criteria that were predefined in accordance with the Scientific Advisory Committee. And these criteria were reasonable flux, exposure time. I mean, by reasonable flux, I mean such a flux that would be such that the exposure time would be reasonable. The availability of HST or fuse archival data, availability of VLT data in some cases, targets that were also proposed by the community. There was a call for proposition by the STSCI to the community at large to make suggestions to observe different types of targets. The final, so the rotational velocities of stars were also an important criterion. And so the rotational velocity were tracked down from the literature for the shortlisted targets. The final down selection was performed to get the best trade-offs between the scientific value of the sample. And by scientific value, I also mean that we wanted to avoid peculiar stars, like, for instance, magnetic stars, because they, although they are very interesting by themselves, they bring little information on the global properties of the stars at these metallicities, for instance, because they are peculiar again. So they can be observed in separate programs that could be related to Ulysses, but they are not part of Ulysses. The other priority was to target stars with partial UV coverage at medium resolution in the archives, so that we would improve at the same time the spectral coverage and the resolution, if possible. The other priority was to give more weight to targets that were proposed by the community at large, and also, again, the exposure time had to be optimal. So the focus was put on O stars with at least, we wanted to have at least 4 stars per spectral type luminosity class beams. And this was to ensure that we could sample properly different rotational velocities, which have an important interest for people working on stellar evolution, for instance. And the goal for B to B5 stars was to have 2 to 3 stars in each class. So, so this is a map, or not a map, but a picture of the SMC, and superposed all the crosses, the pink crosses, are the targets that will be observed within Ulysses for the SMC. So you can see that there is a relatively uniform coverage of the SMC. There's an emphasis on NGC 346, the giant H2 region, that was several times proposed by members of the community as an important target. 222 orbits will be devoted to the SMC. 140 will be with GAUSS, including 49 orbits with the 1096 settings. So these settings that cover the spectral region down to around 1,000 angstrom, thus providing lines, as I told you before, such as the P5 and the O6 super ionization through X-rays. 82 orbits will be observed, will be devoted to STIS observations. I think that's about it for the SMC. Very much the same comments for the LMC. Again, uniform coverage of the whole galaxy. Same settings. I mean, everything like for the SMC. So here I show you on these diagrams how well we sample the spectral types and luminosity classes for the Magellanic Clouds with Ulysses. So in blue, stars that are to be observed, and in red, those that were already in the archives. And one thing that you can note, I guess, immediately is that the SMC was much better covered than the LMC in the archives. And the reason for that is that, first of all, people think the SMC is a little bit more interesting in terms of going down to lower metallicity, and also, and mostly, which is important for UV observations, the reddening is much lower in the SMC than in the LMC, making the observations much more easy in the SMC than in the LMC. I'd like to draw your attention to the very small number of very early type stars in the SMC, so only one star, compared to the LMC. This is a direct consequence of, it's not an observational bias, it's actually a direct consequence of the dearth of such stars, so very early massive stars at low metallicity. And this is a research topic by itself. We don't quite understand the reason why, although there are some recent progress. For instance, there was a paper by Martins and Palacios in 2021, starting to address the reason why we find so few very massive early hot stars in lower metallicity environments. Concerning the observing strategy, so this is a summary of what I just said before. So the FUV coverage is expected to go down from 1140 to 1800 angstrom with COS. So COS is able to deliver spectra with spectral resolution, resolving power, not resolution, spectral resolving power between 15,000 and 20,000. And for the brighter stars, they will be observed with the STIS spectrograph at much higher spectral resolving power, typically between 40 to 46,000. For the coolest stars, so for the coolest hot stars, there will be another mode of observation, which will be the STIS E230M mode, covering the spectral range from 1978 angstrom all the way up to 2800 angstrom at the spectral resolving power of 30,000. So in this table, you see what kind of luminosity class and spectral type bin will be observed with what spectral configuration of HST. So in terms of data products, a quick overview. So high-level science products will be available. STIS and COS calibrated pipeline products and acquisition images, co-added spectra for each grating settings, spliced spectra, so multiple grating settings, multiple instruments. A database is being built as I speak, which will be a repository of metadata that describes the new Ulysses data, the archival or ancillary data, and I will talk about that in a few minutes. And there will be tools like quick look tools to make interactive plots of spectra with interactive signal to noise ratio calculations. There will be a Jupyter notebook for data handling and analysis techniques. And again, so the website is mentioned right there, so don't hesitate to connect. It's full of very interesting data right now. So the Ulysses data releases. So as I said, the first data release was last year in November, and it included 11 and 15 stars, 43 of which were observed as part of the first cycle of the Ulysses programs, and 72 were from the archival and guest observer programs. And there was a research note that was published in the ULLYSES journal. The DR2 was released in March of this year, So it includes 126 stars, so the stars from the DR1 plus 11 new stars, pretty much. And fuse data will be added as in the database very soon now. So NGC stars in NGC 3109, so the images and the photometry are already available, and they will be, so they were in the DR2, as much as the observations of 13 T-Tauri stars in Orion. DR3 is expected for August of this year, so it will include time series spectral projects for classical T-Tauri stars, more LMC and SMC targets with full archival coverage, and obviously newly observed LMC and SMC spectra. It takes time to retrieve the data from Fuse because the Fuse was disconnected from the network for quite some time now. And then by the next data release in August, the spectroscopy of the star in NGC 3109 will be available. A few words about the how you can get to the data. So the Ulysses STSCI website is meant to host and distribute all the data related to the massive star sample. And I'm not gonna. I totally forget the T-Tauri stars. In terms of ancillary data, there are VLT data that are coming. And so I will say a few words about the X-Shooter large program. There's Fuse data, there are more ground-based spectroscopy of Sextans A and NGC 3109 stars that are coming. Model spectra will be available, spectra that are, so models that will be computed with different codes like CMFGen. Wagner is familiar with this one. Power, which is another code very, very similar to CMFGen and Password. So model grids will be available soon for all the stars and more. So the community is encouraged to reach out to the Ulysses core implementation team and also the HST help desk to provide more data for Ulysses targets if they are available. And then in this box, all the URLs where you can download the data. So as I said, there are coordinated and follow-up observations that are planned by the community, and I will say some words about the massive stars one, so the VLT X-Shooter, optical and infrared spectroscopy. So the program was called X-Shooting Ulysses, which I think is a dreadful name. It's very scary. So X-Shoot-U was designed to complement the UV data for massive stars that are being brought by Ulysses. And so the organizing committee of the IAU Commission, G2, so this is the Commission for Massive Stars, they submitted an ISO proposal to gain complementary spectra in the optical and in the near infrared. And the instrument that they selected was X-Shooter. So the spectral resolving power is between 5,000 to 10,000, which is a little bit too low to perform, I think, detailed analysis, for instance, of abundances in some stars. We will need probably more observations with US. Anyway, X-Shooting, so X-Shoot-U is meant to be a single epoch program. And so the whole community organized itself in 13 different working groups that I listed here. And so if you want to join one of them, if you're interested to contribute to discussions and to the work, don't hesitate to join. And so the link is indicated at the bottom of this slide. Okay, so in the few minutes left, I will try to address what kind of stellar science questions can be addressed with Ulysses and X-Q2. So basically, with spectra from the UV to the optical and near infrared, you can measure very accurately stellar parameters, abundances, rotation. You can derive the wind properties, so the mass loss rate, the velocity law in the wind, and the wind terminal velocity, the wind clamping, study weak winds. And you can do this as a function of the metallicity. You can do it in the LMC, in the SMC, and even further down in metallicity in sextants A and NGC 3109. So by doing this, you can study the evolution of hot massive stars as a function of metallicity. But to do this, first you need a critical tool, which is spectroscopic. So to perform this spectroscopic analysis, you need models. And to do this, so we have a group in the X-Q2 collaboration of, it's a very big group. I think it's 40 people working on models that will compute grids and try to improve benchmark models, try to improve the atomic data, the physics in the codes to make the predictions and the calculations of the parameters as accurate as possible and as reliable as possible. So I show you here an example. So in black, so, some spectra of SMC stars of different luminosity classes and spectral types that were observed in the UV, in the optical, also the spectrophotometry of one star. And in red, this is the model that is best fitting each spectrum. So you can see that we can reach a very high level of fidelity right now. So we can gain very accurate information on the properties of the stars. Okay, so again, more spectra and more models. But again, to show you that we are able to reproduce trends as a function of spectral type, for instance, for the different wind profiles that are seen in the spectrum. By doing this, you can study mass loss as a function of metallicity. It's important to remember that in massive stars, the emission peak of the spectral energy distribution is in the UV, and it coincides. So here the model at 40,000 K. It coincides with the wavelength range where the line density is maximum. And through the transfer of momentum of photons to the gas, the photosphere is lifted up and becomes the stellar window. This is why the UV is the best spectral window to study the global properties of stellar winds of massive stars. So theory predicts some dependence with metallicity for the mass loss rate and the wind terminal velocity. And on the left, so you have some theoretical predictions. Those are the lines. So the dashed line is the prediction that is being currently used in all evolution models, and so the full line is a new prediction by new physical models. And so the points in different colors are the mass loss rates that have been measured as a function of luminosity for the largest sample to date to be observed, to be studied quantitatively in the SMC. And so you see that the problem is that there are too few stars that have been observed, and we lack the number that would allow us to discriminate what is a real trend from an artifact that is caused by too small number of objects. Okay, a few years ago, there was a study that suggested that the mass loss rate that were derived using H-alpha spectra for low metallicity stars in galaxies at low metallicity of the local group, some of which are being the targets of Ulysses. So those stellar winds may be stronger than predicted by theory. And this issue is especially disturbing because with the realization that the gravitational wave progenitor black holes have masses higher than 20 to 30 solar masses, this indicates that relatively little mass has been lost during the life of these stars. So, in principle, it would point directly to low metallicity, metal poor environments, and solving this conundrum is therefore considered as a very important issue for the massive stars community. So again, those results were obtained with optical spectra, and in a pioneering study a few years ago with only 3 stars, Wagner, myself, and other colleagues, we showed that probably the conclusions from Trantor et al. In 2014 were wrong. In black, you see the observations, the UV observations of the spectra of one star in the UV, and in red, those are the spectra, the P-Cygni profiles that are expected if we adopted the mass loss rate that were measured from the optical, and clearly this is not possible. So there is clearly a bias in the measure of the mass loss from the optical, and we need to go to the UV, which is the goal of Ulysses, to get reliable mass loss rates. Okay, I had a few slides to say something about testing stellar evolution models, but I think I'm already quite long, so I'm going to skip them and go directly to the summary and prospects. So again, Ulysses is a legacy program of the scale of 1,000 orbits, which brings him to the same level of the Hubble deep field, for instance. But this is for the local universe. So 500 orbits for massive stars and about 500 orbits for young, low mass stars. Ulysses will have a legacy potential for stellar physics, ISM and CGM studies, and for spectral templates for low metallicity galaxies. The Magellanic Clouds and the dwarf galaxies of the local groups targeted by Ulysses, they provide a ladder of decreasing metallicity to study the physics of metal pool massive stars and to extrapolate their properties to those of the population of massive stars found in galaxies like 1Zwicky 18, for instance, or even the first metal-free stars, if possible. So beyond Ulysses, the goal is to go to beyond 10 megaparsecs, and so to be able to obtain UV spectra of metal pool massive stars at such distances, you need a very large telescope, and this is one of the goals of LUVOIR that Wagner mentioned in the introduction. So LUVOIR will be a 15, hopefully, I think, more realistic 12-meter telescope that will be equipped with an instrument that is called LUMOS, which is a multi-object spectrograph in the UV, operating at spectral resolution around 20,000, so pretty much the same spectral resolution, of course, and that will allow us to directly, for the first time, study the metal content in the spectra of massive stars in very distant galaxies and at very low metallicity. 1Zwicky 18, for instance, is 1/30 of the solar metallicity. Okay, I think I'm done there. Thank you for your attention. And if you have questions, I'm real happy to answer them.
Thank you, Jean-Claude. Thank you very much. And for the final view also.
You know that?
A great talk. We do have questions here. I will exhibit for you here. Can you see it on the screen? I have a first question from Thiago Gonçalves.
So I'm gonna stop the.
Okay.
Okay. Thanks for talk. Next one big question is the loading factor of the ring. Aha. As far as I know, there is nothing yet that would connect ALMA to Ulysses. The problem. What do you mean by connecting ALMA data? Because ALMA is sub-millimeter, if I'm not wrong. So it's kind of it's going to be very difficult to measure the mass loss rates, even with ALMA, for non-galactic stars. Maybe you can do it for galactic stars, for a few galactic stars, but for extra-galactic stars, I'm not sure. So is it what you meant?
I don't know if it's also related with the cumulative effects of winds on the dynamics of molecular clouds, the impact on the medium.
Okay.
I would say that not yet, no prospects. But
there is no, well, to my knowledge, there is nothing that has been considered for this yet. But again, I would need to talk to some people, for instance, who are involved in using Ulysses spectra to build spectral templates for spectral synthesis, for instance. Okay, so I meant the pseudodynamics of the clouds in which the stars are found. Well, again, you don't need Ulysses to do that. You can do it in the galaxy, in some cases. So, but yeah, I think it's, why not? I mean, again, it's possible, especially in the SMC. I doubt it, because the SMC is pretty depleted even in CO. But in the LMC, for instance, that might be possible.
okay. We have also another question from, let me let's see here. Mateus, which you know already. Okay. So regarding binary stars, because the galaxies are far, okay, 50 and 60 kiloparsecs, and the others are, I don't know by heart the distance, and there is a problem with the binarity.
Yeah. So we tried to avoid as much as possible binaries, because again, Ulysses will be a single epoch program. So it's hard to observe, to get a scientific value for stars that are binaries with only one single epoch. So for every stars that were pinpoint as binaries, they were redirected to another program that is targeting explicitly binary stars. So it won't be as extensive as Ulysses in terms of number of stars, but at least they will observe specifically known binaries. In our case, we did our best to avoid binaries. This being said, I must admit that for stars in Sextant A and NGC 3109, they are so far away that the aperture of COS is several parsec across. So you can, as long as it's more than binaries, you can have several stars in the aperture. So that's why the pre-imaging was so important, so critical.
Okay. Jean-Claude, we also have a question related to UV versus optical from Karim Menendez del Mestre. And I think you kind of addressed that when you talked about the Tramper results.
Yes.
Because, okay, go ahead. Sorry.
Okay, so the optical is okay to measure mass loss rates when you deal with supergiant stars, and especially in the galaxy, because the wind then is strong enough that H alpha pops up in emission, and then by modeling the H alpha emission, you can directly and relatively accurately infer the mass loss rate. For lower metallicities, the lines they show, the winds are not strong enough, so H alpha is still in absorption. And although there might be some wind filling in some cases, in most of the time the problem is that the stars they are located in H2 regions, and the H alpha is also filled with the emission from the H2 region. So it's very hard to disentangle which contribution is which. Preferentially, you go to the UV, and then you have very clean spectra with very strong PCD profiles for most stars. If you go down to late type massive stars, and Wagner knows that very well, then you enter a regime of winds that is called the weak winds, where even the UV is not enough, where the PCD profiles they vanish, and there it's very, very uncertain what the mass loss rates are.
Okay, thank you. One last question, Jean-Claude. We also have some thank yous from some people here, but one last question from Denise Gonçalves regarding the oxygen 6 line 1032. So
yeah. Okay, so so the 1032 line is indeed, as you know, generated with lots of X-rays. For years, the only way to observe the stars had been fuse, and then fuse has been so stopped in about 20 years ago now. But quite a few years ago, people at the Space Telescope Science Institute, they managed to reconfigure the COS 1096 segments such that they can register all the way down to about 1,000 angstrom. So they can indeed cover the O6 line. So if you want to spot symbiotic stars, I encourage you to try for observing time on HST using this mode of COS. In our case, again, since we avoided binary stars, there should not be any symbiotic stars in the sample.
okay, and just the following from Denise.
Yes. So there is. It is expected that there will be there are actually so two things. There are guest observer programs that are already focusing on some binary stars, and to be fair, in Ulysses we included two systems that are binaries. And for these systems, we will observe them in two different configurations. That's the best we could do, that we could afford, given the limited number of orbits that we were allocated. But yes, there are some programs, some guest observers programs that are being right now working that are focusing on binaries, massive binaries.
Okay. Again, Jean-Claude, I think we have already several questions. I would like to thank you again for your time. It's dinner time in France again.
Yeah, it's gonna
And
be aperitif time.
I can finish the online transmission now. I thank everybody for the questions and for the presence.
Yes.
We will
Thank
end
you.
here, and I will just keep talking with Jean-Claude a little bit, but offline. Thank you,
Thank you
everybody.
for your attention. Thank you for inviting me.
And I will later I will show to you the link for this YouTube presentation, Jean-Claude.
Okay. Cool.
Ciao.
Bye bye. Merci. Thank you.